Hi, I'm Tom Gordon. I'll be talking about our Gantt chart, which is our schedule for the rest of the semester, as well as some of the possible challenges we will be facing up until design day. So our Gantt chart shows some of the main points during the semester, such as the part selection, which was at the beginning of February, and our software coding, which is about to start. If we don't get this stuff completed, we're going to push back our prototype testing, which will also push back our lab testing, which may have problems meeting the deadline for design day. All these things are going to be very important, and they're part of our critical path to finish this project before design day comes up. These are some of the challenges we're going to be facing, such as an overpressure in the system, system response time, sensor calibration, the motor precision, and the use of a standard syringe. Most important is going to be the overpressure. If we have too much pressure in our system, this may cause harm to the animal, and that's one of the main things in our project we're trying to avoid. Anything roughly over 100 millimeters of mercury can cause some type of pain, and our animal rights laws our animal rights laws tell us that we can't cause pain to these animals. So since we're in a lab, we have to abide by all of these laws. Therefore, we have to make sure that the overpressure does not occur. The system response time is also a big problem because, as we saw in the graphs earlier that Cody talked about, the rise time needs to be very, very small. If we can achieve this, we'll be able to get very good data for these tests, which will also lead to better research and development for cures, or possible will lead to cures or possible cures or possible advantages to helping overcome this debilitating disease. Our sensor calibration will also be a very big issue. If we don't calibrate our pressure sensor correctly, we may not receive the proper test data. We are given a leeway of plus or minus 10%, so at low pressures it's going to be very optimal to get the desired pressure almost perfect. If we have too much, we may be at 12 to 13 millimeters of mercury. This is too much for the test results, and the data would have to be thrown out because it will not lead to the desired results that he wants to lay as a standard for his testing. But at higher pressures, we have more of a leeway. We have roughly 16 millimeters of mercury to play with, plus or minus 8. So we have more of a leeway at the higher pressures, which will lead to better results there due to our sensor being able to operate at under 2 psi. Motor precision is also going to be an issue because if the step size is too large, we may be pumping too much pressure into the system, which may cause harm to the animal, which may also put us over the sensor limit, which could cause more problems with the device. And we also touched on the use of a standard syringe. We said that if the rubber dries out on the stopper, it will cause problems with the system, such as leaks, and also the lifetime of these syringes is roughly 12 tests. So if we can get through 12 tests every time, they'll just replace it every 12th test, which will be a good idea, so we don't meet up with any of these problems, such as the sticking of the rubber stopper. And we have a lot of benefits to this project as well. This project will help to research the leading improvement tests for this debilitating disease. This disease is really bad. You basically feel like you want to die. You can't move, your stomach's in pain, your bowel's in pain. You're in a lot of pain. So we're hoping that with this device we'll be able to help Dr. Galligan come up with some means to ease this pain. And as we said, we want to make a very cost-effective model. If we can make a cost-effective model, it'll have a wider availability for smaller university research labs and commercial testing labs, which will help expand the market, which may lead to more research that will improve the treatment options for these patients. Any questions?
Maybe you said this already. The IBS you're talking about is in people, so the studies now are being done with the end goal of helping IBS in human patients?
Correct.
Okay.
Can you repeat the question? I didn't hear. Sorry.
Well, I wanted to know if the end goal was to help IBS in human patients.
Yeah. It's easier to scale up. If we can figure out the cause in the rats, then we can assume that it's the same in humans.
Hey, I have a couple of questions. Since you have a pick in here that's monitoring the pressure sensors, one of your challenges you talked about is overpressure. Couldn't that be automatically detected? And if that threshold is hit, the pick just backs off automatically? Is that, like, I mean, it seems to be just a software.
Yeah, I mean, I guess one of the concerns is that maybe first of all we could have something mechanically wrong with the system where maybe the pick won't actually see an overpressure condition. And the other concern is that you know, the maximum working pressure of the test is around 80 millimeters of mercury, which is like 1.5 psi roughly. So we're half a psi from the limit of the sensor, and so the concern is, well, you know, small electrical fault, or we went over the limit of the sensor. You know, it's something that's made us consider the use of a mechanical,
Like a blow-off valve?
Yeah, like an actual mechanical safety
Yeah.
valve.
Another problem is the calibration.
Blow-off valve that,
Yeah.
you know, would just pop at a certain pressure.
And with the calibration too, you can't really simulate the GI track without having a GI track. Like we're gonna try using, you know, possibly like our hand to wiggle it around to change the pressure, or sand maybe. We don't really know that. We're looking into more ideas for that.
Okay, good. All right, you guys did a good job handling a sensitive subject. Better than I explained it on the first class, so. All right, good. And they ended up with a picture of the